Hello, how are you? All right, so now we're going to do the second part of chapter 7, section 3, which deals with the sampling distribution of the difference in two means. The first part of 7.3 dealt with just the sampling distribution of a single mean. And so I think the easiest way to understand this, this is sort of complicated, but hopefully this will make sense. It may take a bit of practice, is to go ahead and look at an example problem and explain it in the middle of the example. So this one says a farmer has two sets of fields that he uses to grow turnips in. In the north field, all right, the mean weight is 24 and the standard deviation is 3. So that's for all of the ones in the north field. So that would be that mean of 24. So in the north, we have the mean, our population mean, our mu is 24, and our population standard deviation is 3. And then in the south field, the mean weight of the turnips is 20 ounces with a standard deviation of 5. So in the south field, okay, our mean is 20 and our standard deviation is 5. Our sigma is 5. And also I'll call this mu sub n for the mean of the north and sigma sub n. And I'll call this mu sub s for south and sigma sub s for south. And so then it says the farmer takes an SRS, a simple random sample of 50 turnips from the north. And so my sample size from the north, my n from the north, is equal to 50. And my sample size, and he takes an independent SRS of 40 turnips from the south. And so my sample size for the south, my n for the south, is equal to 40. And so, okay, so let X bar sub n represent the sample mean of the 50 turnips from the north field, and X bar sub s represents the sample mean, the sample mean weight of the 40 turnips from the south field. Describe the sampling distribution of the difference. So what happens when we subtract sample means? That is, the deal going on in this section. So let me explain the concept of the sampling distribution of the differences by talking about the sampling distribution of both of these single samples. So let me remind you from the first part of section 7.3. So what we have going on here is this. We've got these turnips that have a mean weight of 24. So in the north field. So in the north field, our mean is 24. So if you were to look at the population, it would be centered around 24 here. So each of these X's represents an individual turnip, the weight of one turnip. Okay, we don't know how it varies. It doesn't say it varies normally or uniformly or anything. We don't know. We just know there's a bunch of X's. Okay, we don't know the population size. It needs to be at least 10 times the sample size, so it needs to be at least 500 turnips. But I think that's a reasonable concept. But then it says we take a sample of size 50 and average them. We take 50 of these X's, and there's a large number of these X's, and average them, and we get an X bar. An X bar, maybe it's like 25.2 or something, okay? Now, the concept of a sampling distribution is we took many samples of size 50, each time finding the average, finding the X bar, and we were to average these things. It would create less variability, okay? It would scrunch them together, and it'd be approximately normal as long as the sample size is bigger than 30. And so that's all the possible values of X bar, okay? The standard deviation of these X bars, as we learned last time, is going to be sigma over the square root of n. So that is going to be 3 over the square root of 50, as we discussed last time. And that's on your formula sheet. So right there, okay? Sigma over the square root of n, all right? So that's for the ones, and the same thing's true, going to be true in the south. So what's happening with the turnips in the south? Well, the population in this case is centered around 20. So here's all the turnip weights. Each X represents the weight of one turnip. Okay. Now, the concept of a sampling distribution is this. We've taken a sample of size 40 and averaged those. We took 40 of these X's and averaged them and got an X bar. Okay. The concept of a sampling distribution is if we did this many times and find many different X bars, many samples of size 40 and average those 40 values every time and came up with an X bar, okay, it would create a family of X bars that we call a sampling distribution. And this sampling distribution will be approximately normal because our sample size is bigger than 30. It'll be centered around 20. And then the standard deviation of these X bars is sigma over the square root of n. So that would be 5 over the square root of 40. Now, what we're doing in this problem is we're subtracting these two distributions in essence. We are estimating if we subtract, all right, now, so if we subtract the mean of you know, if we subtract these two things, it's just going to be 24 minus 20. But what we're doing is we are randomly selecting one of these x bars, an x bar from the north, and randomly selecting one of these x bars from the south, and we are subtracting it. Okay, now we're expecting it to be like 24 minus 20, but there's variability in these x bars, and there's variabilities in these x bars. So this is going to be somewhere around 24, somewhere around 20. So it's going to be somewhere around 4, but not exactly. And we would call that a difference. And if we did this many times, okay, if we took a value here and a value here and subtracted it and got a difference, okay, got a difference. We took a value there and we did it again. We found many different differences. Okay, they would be centered around the difference, around 4. So the mean of the differences is going to be equal to just 24 minus 20. It's just going to be the mean of that minus the mean of that. Okay, so it's going to be 4. Okay, but they will vary. Okay, what about the standard deviation of these differences? Okay, and by the way, so your formula sheet, by the way, would list this difference in that way, the longer way, x bar sub n minus x bar sub s, except it uses a one or two. What about the standard deviation of the differences? How are they going to vary? Well, now you remember when you in chapter 6, when we subtracted distributions, we could subtract the means, but we can't subtract the standard deviations. We have to subtract the variances. In other words, we have to square them, take this, you know, we have to square them, add them, and take the square root like the Pythagorean theorem. Well, so we got to find the variances. The variance of, you know, the variance of the north is just going to be that squared, 3 squared over square root of 50 squared, which is 50. All right, and then the variance of the south is going to be equal to that squared, 5 squared, over the square root of 40 squared, which is 40. And so then we would say the variance of the north minus the south, you would add the variances here. 3 squared over 50 squared, and then plus 5 squared over 40, like that. Like that. That's what you would do. And so, of course, we did that in chapter 6. Even when you subtract here, you still add the variances like that. And so the standard deviation of the differences, in this case, is going to be the square root of that, 3 squared over 50 plus 5 squared over 40. And so, and that's how that formula is derived. And if you didn't understand that, I mean, that's okay. You just got to plug it into this formula here. So the mean of the differences, you just subtract the means. But there's the formula for the standard deviation, which is what I just did in essence. And so anyway, so that's the theory behind what is going on here. So describe the sampling distribution, which so we have to cost. We would say, well, the center, have to describe the center, the unusual values, the shape, and the spread. The center is described by the mean. All right, so the mean of x bar sub n minus x bar sub s is just going to be, you just subtract the mean of, you know, x bar sub n minus the mean of x bar sub s. And so in that case, it's just going to be 24 minus 20, it's 4. So that's the mean. To describe the spread, that's the standard deviation. And so that's just, and I wrote that formula right there, actually. So it is just going to be, so sigma of the difference, x bar sub n minus x bar sub s, is just going to be equal to the square root of, that would be 3 squared over the sample size, 50, plus, and then that would be 5 squared over 40. And so when you do that, you would get 0.897218, approximately like that. All right. And what about the shape? Okay. What about the shape of our sampling distribution? With means, as long as both sample sizes are bigger than 30, and I wrote that right up here, is you have approximate normality if one of two things is true, either of these two things. If it says your populations are in both of them, there's 2 of them, in this case, one in the south field, one in the north field. If it says they varied approximately normally, or if both sample sizes is larger than 30. So if you have small sample sizes, it has to say things vary approximately normally, okay? So anyway, so our shape here, both our sample sizes is bigger than 30. So you'd say approximately normal is our shape, approximately normal, because, you know, n sub north is equal to 50, and I'm sorry, you can see that, and n sub south is equal to 40 are both greater than 30. They're both greater than or equal to 30. And that is a result of by the central limit theorem, which we talked about last time. That's what the central limit theorem tells us. And so now we can use normal CDF or inverse norm with these problems. So let's look at this. What's the probability that the sample mean from the north field will be at least 3 more than the sample mean from the south field? So our sampling distribution of differences, as we just talked about, is centered at 4. So it is centered at 4. So this is normal. There's our differences. And so this is our differences. And we are going with north minus south, or north minus south. So what's the probability at least 3 more than the south? Well, 3 is about right here, we would say. And it'd be 3 more than, so more than will be up here. And so the way I can find an area in a normal curve, as we've done many times, is normal CDF. So we would say normal CDF from 3 to infinity, our mean is 4, and our standard deviation is 0.897218. So that is my lower bound. That is my upper bound. That is the mean of my differences. I'll just put D for difference. That is the sigma of my differences. And so there we go. And so let's use our calculator to find this. I'm certainly expecting this to be more than 50%, more than 0.5, because it takes up more than half the curve. And so here we go. So we'll say second VARS, which is distribution, and go to normal CDF, then go from 3 to infinity. So our mean is 4 and our standard deviation is 0.897218, like that. And so we would get 0.86748. And so that is how you those are the concepts in the last part of 7.3. If you got any questions about that, please let me know. I wish you much luck in regards to sampling distribution and the sample of 2 means. Thanks for watching the video.